Now, you might be asking yourself, can we combine multiple transformations in the same problem? I mean, we've learned about horizontal compressions, we've learned about reflections over the x and y axes, we've learned about horizontal and vertical translations, up, down, left, right. Can we do all of this together? Well, you bet your bottom dollar we can. And I'll show you with this problem here. Let's say we want to graph k of x, which is the absolute value, negative of the absolute value of 2x plus 8 plus 1. To graph this, I'm going to think about the parent function, just plain old absolute value of x, and I'm going to consider what series of transformations could lead from the parent function to this guy, that guy, that guy. So let's get started. So I'm going to think of just the parent function, absolute value of x, and what are some points that we know on this curve? Well, we know if I plug in -1, I get the absolute value is 1. If I plug in 0, I get the absolute value of 0 is 0. And if I plug in +1, I get the absolute value is 1. So what's the first thing we can do to make this more like that? Well, the first thing that comes to mind to me is we can multiply this x by 2 on the inside. We already know that this is going to be a horizontal compression by a factor of 2. Okay? So we could take this to 2 absolute value of x. And what points are going to be on this curve? Well, now if I plug in -1, I get the absolute value of 2 times -1. The absolute value of -2 is +2. So I know the point -1, +2 is on the graph. Similarly, 0, 0 is still on the graph. So if I plug in x equals 0, I get the absolute value of 2 times 0, which is 0. And 1, +2 is also on the graph. All right. So next thing I could do to make this look more like that is in parentheses, I can add 4 to the x. Now why 4 and not just 8? Remember, these operations that are done to x on the inside have to be done in parentheses. I need a 4 here, because when I distribute this 2, that'll give me that 2x plus 8 that I had there. Right? In other words, this original function is equivalent to negative absolute value 2 comes the quantity x plus 4, and then close the absolute value plus 1. So it's plus 4 and not plus 8. Okay. And just like this was a horizontal compression by a factor of 2, let me write this here. This is going to be a horizontal translation. And remember, this works kind of the opposite of the way we might think intuitively, which is that if you add 4 to the x, you're translating left by 4. Right, a horizontal translation left by 4. Okay. So if we know these 3 points were on this curve, then we can get 3 points on this curve by moving each of these points left by 4. So left and right, that affects the x-axis. left by 4 means we'd subtract 4 from each of the x values. So instead of negative 1, 2, I have negative 5, 2. Instead of 0, 0, I have negative 4, 0. And instead of 1, 2, I have negative 3, 2. Okay? And then we can check these values by plugging in each of these x values and making sure we get each of the y values. So if I plug in negative 5, and negative 5 plus 4 is negative 1, times 2 is negative 2, absolute value is positive 2. Plug in negative 4, negative 4 plus 4 is 0, 2 times 0 is 0, absolute value is 0. If I plug in negative 3, negative 3 plus 4 is 1, 2 times 1 is 2, absolute value is 2. Okay. Well, what's next? We also have this negative sign here. A negative sign out front we know is going to be a flip over the x-axis. Okay. And if I flip over the x-axis, I negate each of the y values. So 3 points that are on the graph of this curve here are going to be negative 5, negative 2, negative 4, 0, and negative 3, negative 2. I took each of these y values and I negated them. Finally, plus 1 at the end. That takes us to the function we want to graph. And if we do a plus 1 at the end of the whole function, that's a vertical translation up by 1. Okay, so a vertical translation, that's going to affect the y values again. And we'll be adding plus 1 to each of these 3 y values. So we should get negative 5, negative 1, negative 4, 1, and negative 3, negative 1. And we'll just plot these 3 points and sketch the graph from there. So left 5, down 1. That's our first point. Our second point, remember the second point came from the vertex, meaning the thing in the middle of the original absolute value. So we expect that this will still be the vertex of our new graph k of x. So that's at negative 4, positive 1. And our third point is negative 3, negative 1. So left 3, down 1. We can connect the dots and we get a V shape. So notice that this graph, for one thing, it's upside down from a standard absolute value function. That's because there was a negative out front telling us to flip over the x-axis. It's a little compressed because we have a vertical compression by a factor of 2. And it's been translated 4 units to the left and 1 unit up. So the vertex is here now. Let's do one last check, make sure we did everything okay. So what can we do to check it? We can plug in the 3 x values that we obtained, namely negative 5, negative 4, negative 3, and make sure that we get these 3 y values. Okay, so k of negative 5, well, that's negative quantity to negative 5 plus 4 plus 1. So negative 5 plus 4 is negative 1. This is a negative quantity. 2 times negative 1 plus 1. 2 times negative 1 is negative 2. And what's the absolute value of negative 2? It's just positive 2. So we get positive 2 in here, but we still have this negative outside. And then negative 2 plus 1 is negative 1. So this means negative 5 comma negative 1 is indeed on the graph, just as we thought. So this checks out. Next check. K of negative 4. We expect that to be positive 1. Is it? Well, let me erase this and we'll find out. Okay, so K of negative 4 is negative quantity absolute value 2 times the quantity negative 4 plus 4 plus 1. Negative 4 plus 4 is 0. We have negative quantity absolute value of 2 times 0 plus 1. Well, this is 0. The absolute value of 0 is 0. Negative of 0 is just 0. So we have 0 plus 4 is 4. Whoa, sorry. Mistake there. 0 plus 1 is 1. Good eye. Okay, so negative 4 comma 1 is indeed on the graph. And our last point we want to check is negative 3, negative 1. So K of negative 3 is the absolute value of 2 times negative 3 plus 4. I'm just plugging negative 3 in for x, remember? Plus 1. So negative 3 plus 4 is negative 1. 2 times negative 1 is negative 2. Take the absolute value and you get positive 2. Positive 2 times that negative outside takes us back to negative 2 again. And we do indeed get negative 1, which means the point negative 3 comma negative 1 is on our graph. All right, thanks for watching, and I hope this video helps you understand how all these transformations, like translation, horizontal compression, and reflection, how they all work together to affect and transform the graph of the original parent function to a more complicated function. Thank you again.